Uh, at the bottom, there is a.
Oops. Yeah, I memorize the whole thing. Stop my video. Yeah. So here is about this. And the idea is very simple. Think of taking a needle and think of taking, let's say, a piece of thermocol or even, clay that the kids play with. And take that needle and make a scratch in the thermocol or make a scratch in the clay. And it's very easy to do that, right? We can do that with a very little amount of force. The same amount. Try to make scratches on the stainless steel dishes that we use, dishes in the kitchen. And it's likely not be enough to make. Or if you make a scratch, it will be. Whereas on the clay, you could make that for. You could do a very ask you which of the materials is hard and which is soft. It's very easy to classify them. You will be able to tell me, irrespective of the background, that the steel vessel is hard and the clay is soft. Right? Now, that's as far as qualitative understanding is. I say, well, let's quantify it. To quantify it is the voice issue is still not resolved, says Prakash. Okay, Prakash. So I am going to.
Yes, ma'am. Because your sentence is like coming 2 or 3 times. Means same sentence. It is like coming 2 or 3 times and in breaking.
Do you have a earphone?
Let me just. I do have an earphone, but usually people say that with the earphone the voice comes out lighter. But let me just get the earphone and try, okay?
That
Here
sometimes
is what I'm
helps.
going to do. Yeah, I'm going to stop sharing this. And I'm sorry, give me a minute. Let me get the earphone. I usually don't have this problem. And at my end, it's showing me that the network is fine. It's not even unstable or
But now,
something.
ma'am, you are talking. But now you are talking, na, ma'am. The
Yeah.
voice is very clear.
Ah.
Now it is very clear.
Okay, so maybe it's a distance. I will also try keeping the laptop at this distance from me and then talking. Okay, so
Okay,
let me get the earphone.
okay, ma'am.
Yeah. Okay, is this clear? Try the earphones once.
It is clear, ma'am.
Hello?
Yes,
Yeah,
ma'am.
we can hear you.
Yeah, we can
Is
hear your
this
voice now, ma'am.
better? Okay.
Yes, ma'am.
Okay, so let's try this and see how this works. Yeah, my phone has a battery of only 30% right now. Let's see how far that goes. Okay, let's go back to our PowerPoint. So here we go.
Some email is seen. Prita, we are seeing some email of. Prita? I'm seeing some email window, not your slides.
It's talking to you about
Yes, now we can see your slides.
okay. Okay. Sorry, people. Let's hope all the excitement for today. So what about quantifying? And I think in all this excitement, and somewhere I have mislaid. Here, okay. So when I was a metallurgy undergrad, okay, so we had a course on minerals, and we were introduced to what you're seeing on your screen right now, something called a Mohs scale of hardness. To do that hardness scale is supposed to do left, right? There is hard going from 7 to 10. And what exactly than talc. So if I take a piece of gypsum and can I scale. But this is still somewhat arbitrary, right? You're saying, okay, somebody took 10 minutes and put them in a 1 to 10 order. Does that work for everything? Does that work for any material that I want to pick up? So what has been used to quantify indents is something called indentation. Okay. And there are two types. So there could be this Rockwell Brinell Vickers, which is micro indentation, and then nano indentation. But the idea remains the same, which is that take a sample, a, a tip, pointy tip made some poke that and divide the load that we used to poke with the size of the imprint, and that is hard. Often make let me try to give you examples instead. That it is basically uh, a very, very sharp tip or a very, very tip with a and the other that you example with Prakash that you and actually Prakash a few details scanning electron microscopy would be deposition, and you can sample. I can what you see here, this pyramid, this is an indent. I can indent within and this phase. See, well, how it is structure here, which is indented. Or you could the work that is cantilever. cantilever with a cantilever structure of the wires. It's a different structure. That's called length scale. Where you have the beam is fairly electron microscope. What they want to this cantilever as a subject as a okay, so now I take cantilever, which is otherwise flat, and put it in a sample of water or put a few drops of water in it. If it has the pollutants that I'm trying to detect, the cantilever will bind with those pollutants and it's going to bend. And I can calibrate the bending of this cantilever to figure out how much pollutant there in the water sample that I've just put on the cantilever. Okay. Now, all of this bending is a function of the stiffness of the cantilever. So you need to know what the stiffness of the cantilever is. And because the cantilevers themselves are very tiny, stiffness, you need and so they use a nanopliers to bend the cantilever and create this force versus displacement curve and the reflection displacement curve of the cantilever. Okay, but even before they made the cantilever, they wanted to figure out what kind of a big which is very material. Prakash has been working with that, which is very carbon to it. Carbon and function of adding carbon, how do the properties of this polymer change? Okay, so these are some experiments that they did in the nanoindenter where you add carbon to the polymer, the film of it. Now this film, it's not free hanging in air. Okay, so you make a film on top of something. It could be a glass slide, it could be a piece of silicon. You make a film on top of it and you indent from the top. Okay, and these are some examples of indents where you apply a load and you measure the displacement again, except that you load, hold it at the maximum load, and then you unload it and you do some analysis on this unloading, which is where we are headed today. But because this is a film sitting on top of something else, these are two materials and you are indenting from the top, depending on how deep you indent, you could sample, if you look a lot here, and you can consider it as equivalent of stiffness. And the right side is hardness that I was talking about, load over area of the imprint, right? And if you see, these squares are stiffness, and what you see is when the depth of the indent is very small, 820 nanometers, you are measuring. As you go deeper, 200 nanometers, 220 nanometers, the stiffness increases. Now, for a particular material, if you think of a spring change with how deep you go into the spring. It's not a depth dependent property. But what's happening here is that at low depths, you are only the upper layer, which is but you are so make is that there is an experiment, there is data, and then there is analysis. And sometimes that analysis is purely statistical. You analyze even you need to know the physics of. You cannot just say, oh, times that doesn't work. The physics all just say all the times that doesn't work. What are for today? You can get values which are now independent of it. From our work. Can you guys still hear me clearly? Any problem?
It is on and off, Prita.
Then
Maybe,
it's in
maybe.
the on.
So
It's
maybe
it's
switching
still on and
off
okay. I'm
the
going to
video
say
would help because I still think it is network
on and
related.
try. Is this better? Is better?
Yeah, it's better,
Yes. No.
but it goes
Okay.
on and off. I mean, sometimes it is very clear.
Still
Sometimes we
goes.
just keep hearing the same sentence at a faster speed. Sometimes even twice after the
Oh.
sentence. So
Still goes. Yes. Okay. Okay. Let me finish this slide, and I'm really sorry about this.
Ma'am, I
Okay.
think
Let me
it's a
continue.
bandwidth
And
issue
is
yeah,
because
I think
sometimes it is a message.
uh, I think
So
it is a
I
okay. So
bandwidth issue.
I'll again
Probably if you
turn the
remove
video
video,
off.
it will be better. Yeah,
Yeah,
yeah.
I will again turn the
yes,
video
ma'am.
off because anyway the rest of it is very sort of slide specific. Okay. So Tejas or Prakash, tell me if things. What I do. It's just going to make the other spaces in the house. Let me try. This was where we took a sample of zirconium, and we wanted to see that. So what you see top, these lines are what are called boundaries of various types. Again, so Lawrence wanted to say effect of these boundaries. So he made samples. I don't know how well you can see the top right. Those of you who are from mechanical think of lathe milling, okay, or engineering where you've done a workshop, right? So think of lathe milling, and now think of doing lathe milling with a beam of ions and not with a tool. So this is exactly milling, where we take a bulk sample and we use an ionic beam to cut out the neighboring region, leaving a pillar standing, which is what you can see here labeled as orientation 2. And then we take these pillars and again we use this tip to compress the pillar. Okay. And when we do actually the behavior of pillars, individual pillars, various things. Want to develop things, unconditional response and so on. Okay. So in the absence of a video, here is the machine. It is going to and it's to response. But we zoom in here, and if you zoom in here, you see here is where all work happens. Okay. So this is what is called a transducer. This is the heart of. Oh, Prakash says that there are still problems. Prakash, the problem is that I cannot change where I am.
Half of it, cut half, cut off, cut a half, please.
Sorry, just give me a second.
Cut half.
Okay, so I've tried switching to a different network or a different whatever stream of the same network. Is this any better?
Yes, ma'am. This is working fine.
Okay, okay, good. Okay, so let me just restart with the description here. See, again, I mean, this has absolutely no relevance analyzing data where the data came from. Okay, so what you label here as Berkovich tip, that's the diamond tip which we indent. Okay, sorry. So this is the thing with which we indent. Okay, this is our sample. You see a glass piece. This is could be a quad sample, and this is a transducer. This do all the load and displacement measurements. Okay, and here is a schematic of what the tip looks like. Okay, it's a three-sided pyramid, and ideally 3 planes should meet in a point, and this included angle between the z-axis and the median of one of the faces should be exactly 65.35 degrees. Okay, and the reason I want to show you a schematic of a perfect tip is that we will address the issue that of course the tips that we buy from the market are not perfect to begin with, and as we use them, this end of the tip, which is doing this poking indenting, gets worn out. So we need to correct for those effects when we analyze the data. Now, when we do this experiment, what actually happens, and this is where we now get into, you know, the dirt and grime of actually analyzing the data. So this is a tip, and red is a quad sample. We apply a load, the tip goes into the quad sample, and here I need to draw your attention to the details. You see that the tip has gone into the sample to a certain depth, and now we are total depth, and we are giving 2 different labels. So if H is the depth, then there is one HC, and FS of the kids, but it is not actually touching it. This difference is very important, because when I said that we want to calculate hardness, it is HC that we are interested in. How much of the sample is in contact with the tip, because that's what is resisting deformation. The part HS, it deflects, but it's not actively resisting anything. It's just bent. You know, if you take a sheet and you try to poke it with something, it's going to deflect. Okay, and then we unload, and with there is a residual imprint left in the sample, and this from depth of the imprint from the surface is what is HF or H final. Okay, now some of these things we can just directly measure, and some will require some analysis and some math. So this is what is the input given to the instrument. What you see in red is what we specify. This is your control on the experiment. You say, well, load it up to some maximum load. In this case, it's a little less than 10,000 micronewtons. You may want to hold it at that load for some time, or you may not want to hold it, and then we unload. And what we measure is shown in black. That's the displacement response. Okay, so that's the displacement that we are measuring from the instrument, and you can see that H final is labeled here. Okay, now, so you've got the applied load, you've got the depth of penetration. What does this data look like? If I plot now, on the left, what you saw is load and depth as a function of time, and what you're seeing now is load as a function of depth. I keep increasing the load, the tip goes deeper and deeper into the sample, and then I unload, it comes back to some final depth HF. Okay, these terms need a little bit of getting used to. Your data is going to be one continuous set of load values and one continuous set of displacement values. Okay, but to analyze the data, it would be good to have this image in front of you. Okay, that what are we analyzing? So now what we are analyzing is this, right? That I showed you up here in the middle image, that although the tip goes down to certain maximum depth, which is H max, only a fraction of that actually is contacting the tip. Okay. So now if I could zoom in on that part, which is what is shown in the schematic here, this depth C, and cut out a cross section. Okay. That's the cross sectional area that I'm interested in. I'm saying that I apply a load P, and this is the cross sectional area of the imprint that. So I'm going to repeat some of those things here, that this is what we are interested in, right? This cross sectional area. And remember, this is what my ideal tip looks like. Now you could go to an 9th grade geometry student and tell them that, look, I have a tip which looks like this. I know this included area. I know this depth HC, calculate the cross-sectional area, and they can calculate it. It's a very simple geometry problem. Okay. So if we could do that, then we really don't need much of anything else that I'm talking about. Okay. But like I said, our tip is not perfect to begin with. And the second problem is that I don't know what this contact depth is, right? What I measured was only an H max, right? I measure a total depth. I apply a load, the tip goes in. So my first job is to separate this H. And I could subtract this HS, I have my HC. And then I need to figure out the cross-sectional area if I could first figure out this contact depth. Okay, so what was said was that, well, you can get this HS by this formula, 0.75 multiplied by the maximum load divided by the slope of the unloading curve. This is where our work starts, that we have unloading data to calculate the slope of that unloading curve so that we can put it in here and get our contact depth. Okay. And once we get that contact depth, like I said, well, if the tip was perfect, then calculating this projected area would be very easy. Okay, that projected area would be √3/4a square, where a would be the edge of that equilateral triangle. And you can relate a to this depth HC because you know that this angle is exactly 65.35. So you would have this equation, 3√3 tan square this into HC square. And our job would be done. The problem is my tip is not a perfect pointy tip. My tip is blunt. And the bluntness keeps changing as I more and more. So we need to correct for that. And one of the ways to correct for that is to include these correction terms. Now, we don't have to do that today. I think, right, Prakash, this is all known. I mean, we are going to just give you these constants. But
Yes,
this
ma'am.
is part of doing the indentation experiment, that the very first thing that you have to do is figure out what these correction constants are. Okay. Once you figured out what these correction constants are, you can calculate this P max over AC, provided you know this slope of the unloading curve. So now we are going to dwell a little bit the unloading curve part. I think. Oops. Gosh, I messed up the animation. This image was supposed. Sorry.
Okay. Okay.
So,
Okay, ma'am.
yeah. And our job is to calculate this S, right? So, okay, it's a little bit about S part first. Look at the second point first, and I'll come to the first point later, even though you'll have to do that first. So, here is what you do, right? You have unloading data. You fit a function to it. Conventionally, we fit a quadratic equation to this, and we take the derivative of that quadratic equation. We evaluate then that derivative at the maximum load, and that gives us S. S is the slope of the unloading curve. But that doesn't always work, and I'll show you why that doesn't always work. But even before you can do this, you have to take a closer look at the kind of experiment that you're doing, okay? So what happens is, remember there is this tip which is going into the sample and I'm measuring displacements. In addition to displacement into the sample, we have drift. Drift due to doing these experiments at, let's say, 23 degrees at which you are maintaining your lab. So the edge that we measure, the depth that we measure, is depth of penetration into the sample plus movement of the tip due to thermal drift. Okay. Now, for experiments which are done over a short period of time, you don't have to worry about it because the instrument, or rather the software that runs your experiments, is set up to measure this drift before the experiment. So what it does is it has a very small load. So here is the plot, right? That you measure displacement as a function of time. And as you can see that this is a linear fit to it, a straight line fit, right? And the equation is given up there that you can just fit it as H is equal to M into T plus C. And you figure out M and C as fitting constants. And once you know those fitting constants, for any time, you can figure out what is the contribution of drift to the total displacement, and you subtract that. And you say the rest is displacement into the sample. The rest is actual data that I'm going to work with. And again, drift or displacement as a function of time. And you notice that this is not quite linear, right? The red line again is a linear fit. And if you take this fit and you do this correction in your data, you're probably going to not be correct. Okay. So point number one, be aware of the corrections to the data that are already done by the software that you're using. Point number two, don't completely trust that correction. Evaluate for yourself whether it is working for your experiment or it isn't working for your experiment. We found out that it doesn't work for our experiment. Okay. So what we did was we introduced a new way of correcting for drift. And this was actually done by a PhD student who's now graduated, Sandeepan Chattaraj. And what he did was he said, look, I'm going to measure displacement at the beginning of my experiment. And I'm also going to measure displacement at the end of my experiment. Okay, you see a small orange line here, which is post monitoring. And then I'm going to plot both of these, pre as well as post, displacements as a function of time. And what we found was that if we now fit this not to a linear equation, but to a quadratic equation, that works very well for us. Okay. So I think that's the first thing that you're going to do is you're going to do a quadratic fit to the drift data, figure out what these fitting constants are, use those fitting constants to correct your data. And now you have a set of data which is devoid, which has been cleared of all thermal effects and represents only the behavior of your sample. Now you are ready to start using that data. Okay, so this is 0th level correction and it does become important. If you can see that black and red is whether or not you correct for and whether or not you use the right kind of function to correct.